Let's talk a little bit more about the ideal gas processes, but now from the point of view of energy. So with these ideal gases and the processes of expansion or compression or heating or cooling that we've been talking about so far, there are really just a few types of energy and a few ways that energy can change that'll be of interest to us. So we're going to define a quantity called internal energy, which might be a little confusing because it seems like it might be better named heat, just from how we typically use the term heat. So internal energy is the total energy of all the gas particles in the system. So that's going to be the kinetic energy of the gas, and if there's electrostatic repulsion between gas particles or attraction between gas particles, we'll have some electric potential energy there. We've got rest mass energy. That's the energy in the form of matter in this thing. For the processes we're going to be looking at, though, we assume with an ideal gas that the interactions between particles are zero unless they're colliding with each other. So that electrostatic potential energy, that's going to be roughly unchanged with this assumption. And we're assuming that we're not going to be undergoing any process of radioactive decay or nuclear fission or fusion during these processes of compressing or expanding gases. So we can ignore what we call the rest mass energy. And so in these ones, the internal energy is really just going to be the only part of it that we care about anyway, is going to be the total kinetic energy of the particles that make up that gas. And so that internal energy is going to correspond very closely with the temperature of the gas. Now, heat, in our typical understanding of the term heat, might seem like a better name for that. But actually, heat we're going to need a little more specific name for now. So when we talk about heat, we're only going to be referring to something as heat when it's energy that's being transferred. So energy that's just sitting in a gas, that's not going to be heat, because it has to be energy that's being transferred from a warmer to a colder object. So that net flow of energy that happens because of collisions between the particles, we'll call that heat energy. But it's just a transfer, just like work is a transfer of energy, and that's our other term that we're going to be using here. Work will be the energy given to a gas as a result of some outside force applied over a distance on the gas. So it's easiest to envision this all using that familiar piston example. So we have some internal energy, U, of the gas inside here. If we add heat to our system, then we can cause a change in U. If we take away heat from the system, then that can cause a change in U as well. Now, adding heat, the only way that we could do that is if we have something warm on the outside here, warmer than the inside gas particles, because remember, heat has to be energy that's transferred from warmer to colder objects. So if we want heat to go into this system, we need warmer objects on the outside than the colder gas on the inside. And if heat's going to be leaving this system, then this gas has to be warmer, and we have to have cooler matter on the outside. Work, we're going to say, is we'll call positive work that is being done on the gas. So that happens when we push down on the piston here. When we compress that gas, we apply a force downward, and that causes a downward movement of the piston. Negative work, then, we'll say, is either work, we can think of it as work when we're pushing down on this piston, but the pressure in the gas is too much here, and it pushes upward, so we're applying a downward force, but the displacement is upward. That's negative work. Or we could think just of negative work as being work that this gas does on the piston or does on the surroundings. So we can look at this in terms of something called the first law of thermodynamics, which we've actually worked with before. It's just the conservation of energy. It says that energy can't be created or destroyed. So if we look at this system again, the conservation of energy in this case says whatever value of U that we start with, internal energy that we start with, and I guess I should mark here internal energy, we use the variable U, heat we use a Q, and work we use a W. So whatever value we start out with for internal energy, U, the ending internal energy will be the starting one plus whatever heat enters or minus whatever heat leaves that gas, and plus whatever work is done on that gas or minus whatever work that gas does on its surroundings. So we can write this as the change in internal energy is equal to the work done on the gas plus the heat that enters that gas. Now if heat is leaving the gas, then this Q value would just be negative. If the gas is doing work on its surroundings, then the value for work will just be negative. So now let's look at this equation. Delta U is equal to Q work plus heat. Change in internal energy is equal to work plus heat. Let's think about what delta U will be, whether it will be positive or negative, what work will be, and what Q will be, positive, negative, or zero, for each one of these different expansions and compressions we've talked about. So with isobaric expansion, first of all, isobaric, this is actually probably our trickiest case. So here the change in pressure is equal to 0. We're going to keep coming back to the ideal gas law with all of these. PV is equal to nRT. So in isobaric expansion, well, the word expansion tells us that container, that space is getting bigger. So if we go back here, anytime we have expansion, that means that our piston is being moved upward, so work is negative. So I'm just going to go through here. Anytime I see the word expansion, I know that work is going to be a negative value. So expansion there is negative, and work here is negative. And let's see, back, oops, isochoric, okay, I forgot one up at the top here. So in isochoric heating and cooling, the volume stays constant, so here work is going to be 0, 0. With compression, work is going to be positive, work is positive. And then down here at the bottom, work is negative for expansion and is positive for compression. Okay, so we've got all our W's figured out for all these different cases, just from whether it's an expansion or a compression or neither of those. Okay, so again, delta U is equal to Q plus W, and PV is equal to nRT. Okay. Let's see, we were working on isobaric expansion. So we know that work is negative in this case, and for isobaric expansion, our pressure is going to be constant, and so volume is going to change as temperature changes. So if our volume is getting larger, so here we might write out that V is equal to some constant times T. If our volume is getting larger, as it does in expansion, then our temperature must be increasing. When temperature increases, that means delta U is positive. Internal energy is tied with temperature. So our work is negative, our internal energy is positive. If we look at this expression up here, if our work is negative and internal energy is positive, the only way that can happen is if Q is positive, and it has to be more positive than the work is negative. So Q here has to be a big positive. We have to be adding a lot of heat to this system, more heat than we have work coming out of this system. And then the opposite is true as well for isobaric compression. When our volume drops, temperature is going to drop as well. So delta U is going to be negative. And so then our heat, in order to make the first law of thermodynamics work here, if delta U is negative and work is positive, then Q has to be a negative, and it has to be more negative than this work is positive. So Q has to be a big negative there. Okay, now up here, isochoric heating. Well, anytime we have heating, that means that temperature is going up, so delta U is positive, and that's going to happen only if, so work is 0, delta U is positive, Q has to be positive as well here. So we have to have the same value for Q and delta U in isochoric processes. So in cooling, the change in internal energy, that's going to be negative, and the Q value, the amount of heat added, is going to be negative, so really heat is moving out of the system for isochoric cooling. Then down to isothermal, so let me just write here, delta U is equal to Q plus W, and PV is equal to nRT. So in isothermal expansion, temperature stays constant, so we get this relationship that PV has to be a constant here. Okay, so in expansion, our volume is getting larger, and so we had the work that was negative for that one. If it's isothermal expansion, that means that the temperature doesn't change, so that has to mean that internal energy doesn't change either. So delta U is 0, so if we've got 0 is equal to Q plus some negative value, then Q has to be a positive value. It has to be the same positive value as work is negative here. And again, isothermal over here tells us that internal energy doesn't change. U, not a V. Okay, and so Q must be equal but opposite to the amount of work done on that system for isothermal processes. And then adiabatic expansion. Just delta U is equal to Q plus W. PV is equal to nRT. Okay, one of the pieces we had for the definition for adiabatic expansion or adiabatic compression was that this had to be a really rapid process. So rapid, in fact, that we can't have any heat transferred at all. So Q is equal to 0. So if work is negative and Q is 0, then delta U has to be negative. Delta U has to have the same value as work in this equation. So if work is positive and Q is 0, then delta U has to be positive as well. So this chart might be a good reference for you. It just lays out everything that we had so far. So for isochoric, that's constant volume, heating or cooling. For isothermic, that's constant temperature. Or for adiabatic expansion or compression, those three all have one of the values in this chart that's equal to 0. The only one that doesn't here is constant pressure expansion and compression. In that case, we have all three of these values have some non-zero value. So again, this would be a good thing to have handy to reference, but you're not going to have it on the AP test. So you really do need to be able to think through, why is isochoric heating? Why is that work of 0? Well, because volume isn't changing, so we're not changing we don't have any distance on the piston, and so force times distance gives us just 0 here. You need to be able to think through those processes. So use the table as you're working, but don't rely completely on it. Kind of start working through those processes as you're playing around with these different heating, cooling, expansion, and compression processes in our practice problems and on our assessments.